Welcome to the lecture on dynamic programming. This lecture is for chapter 8 of our course Operations Research. Dynamic programming is a mathematical technique which deals with optimization of a sequence of decision process, the process in which a sequence of decisions is taken. Mathematically, a dynamic programming is a decision making problem of n variables, the problem being subdivided into n subproblems, and each subproblem is a decision making problem of one variable. The solution of dynamic programming problem is achieved sequentially, starting from the initial stage and then proceeding to the next stage and finally to the final stage. The chapter contains two modules. So, we will start now our discussion on module 1 of this chapter. Let me first explain what a dynamic programming is. Suppose that a company has to decide the production plan of an item for the next 3 months, so that the demands are made in the 3 different months at the minimum cost. If we consider these 3 different months as stages, then this problem is in fact a multi-stage problem. For such a problem, decisions are made sequentially over several periods using a technique called dynamic programming technique. In dynamic programming model, the current decisions influence both present and future periods. Dynamic programming approach divides the problem into several subproblems which are solved sequentially until the original or initial problem is solved. The characteristic of dynamic programming model is expressing the decision problem by means of a recursive formulation. Thus, dynamic programming is a mathematical technique dealing with the optimization of multi-stage decision process. It is called dynamic because it is particularly useful for problems where decisions are taken at several stages, such as every day or every week. The word programming has been used in the mathematical sense of selecting an optimum allocation of resources. In 1950, Richard Bellman developed this technique, and this dynamic programming technique can also be named as recursive optimization. Let us now define some terminologies which are usually used in dynamic programming. Stage: the point at which a decision is made is known as stage. The end of a stage marks the beginning of the immediate succeeding stage. For instance, in replacement problem, each year is a stage, whereas in shortest route problem, each city represents a stage. State: the variable which links two stages in a multi-stage decision problem is called a state variable. At any stage, the values that state variables can take describe the status of the problem. The number of state variables should be as small as possible, since larger the number of state variables, more complicated is the decision process. Optimal policy. A policy which optimizes the value of an objective function is called an optimal policy. Principle of optimality. The principle of optimality states that the decision from one state in a stage to the end is independent of how one actually arrives at that state. Bellman's principle of optimality. This principle states that an optimal policy has the property that whatever the initial state and decisions are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. This principle implies that a wrong decision taken at a stage does not prevent from taking optimal decisions for the remaining stages. Return function. At each stage, a decision is made which can affect the state of the system at the next stage and help in arriving at the optimal solution at the current stage. In fact, every decision has its merit, which can be represented in an algebraic equation form, and this equation is called a return function. The return function generally depends on the state variable and the decision made at a particular stage. Now, we will explain the characteristics of dynamic programming, that is the basic features which characterize the dynamic programming problem, and those are given below. The problem can be subdivided into stages with a policy decision required at each stage. Stages decompose a problem into subproblems such that an optimal solution of the problem can be obtained from the optimal solutions of the subproblems. Every stage consists of a number of states associated with it. The state of the system at a stage is described by a set of variables we call as state variables. When the current state is known, an optimal policy for the remaining stages is independent of the policy of the previous ones. To identify the optimal policy for each state of the system, a recursive equation is formulated with n stages remaining, given the optimal policy for each state with n-1 stages left. And finally, using recursive equation approach each time, the solution procedure moves backward stage by stage for obtaining the optimal policy at each state for that particular stage till it attains the optimal policy beginning at the initial stage. We now state the dynamic programming algorithm. The computational procedure for solving a problem by dynamic programming approach can be summarized in the following steps. Step 1, identify the decision variables and specify objective function to be optimized under certain limitations, if any. Step 2, decompose the given problem into a number of smaller subproblems. Identify the state variables at each stage and write down the transformation function as a function of the state variables and decision variables at the next stage. Step 3, write down a general recursive relationship for computing the optimal policy. and then decide whether forward or backward method is to follow to solve the problem. Step 4, construct appropriate stages to show the required values of the return function at each stage. And finally, in step 5, determine the overall optimal policy or decisions and its value at each stage. There may be more than one such optimal policy. Notes: generally, the solution of a recursive equation involves two types of computations depending on whether the system is continuous or discrete. In the first case, that is, if the system is continuous, then the optimal decision at each stage is obtained by using the usual classical method of optimization. Whereas, in the second case, that is when the system is discrete, a tabular computational scheme is followed. Note 2, if the dynamic programming problem is solved by using the recursive equation starting from the first through the last stage, that is, if we obtain the sequence f1, f2 up to fn, then such a computation is called forward computational procedure. And if the recursive equation is formulated in a different way so as to obtain the sequence fn, fn minus 1 up to f1, then the computation is known as backward computational procedure. Until now, we have discussed the basic terminologies of dynamic programming, characteristics of dynamic programming, and dynamic programming algorithm. We have learned that in dynamic programming, we have to first form the recursive equations. Then the recursive equations are solved to determine the optimal policy. To solve the recursive equations, two computational procedures are usually followed depending on the system, whether the system is continuous or discrete. If the system is continuous, then usual optimization methods are followed, and if the system is discrete, then tabular computation scheme is used. We now proceed to discuss dynamic programming model 1, which considers single additive constraint and multiplicatively separable return. Consider the problem maximize z equal to product j equal to 1 to n fj yj subject to summation j equal to 1 to n aj yj equal to b, where yj is greater than equal to 0 and aj is greater than equal to 0. Here we introduce state variables sj equal to summation j equal to 1 to up to n aj yj equal to b, sj minus 1 equal to sj minus aj yj for j equal to 2, 3 up to n. Let capital Fj Sj equal to maximum of product Fj Yj, where j takes the value 1 to up to j, and the maximum is considered over y1, y2 up to yj. Then the general recursive formula becomes capital Fj Sj equal to maximum Fj Yj into capital Fj minus 1 Sj minus 1 for j equal to n minus 1 up to 2, and also f1 s1 equal to capital F1 S1 equal to F1 Y1. Let us consider an example. Find maximum of Y1, Y2, Y3 subject to Y1 plus Y2 plus Y3 equal to 5, which is a single additive constraint, and Y1, Y2, Y3 are all greater than equal to 0. Here we introduce the state variables S3, S2 and S1, where S3 equal to Y1 plus Y2 plus Y3, which is equal to 5, and S2 equal to S3 minus Y3, which is equal to Y1 plus Y2, and S1 equal to S2 minus Y2, which is equal to Y1. Let capital Fj Yj equal to maximum of the product Y1, Y2 up to Yj, then F3 S3 equal to maximum of Y3 into capital F2 S2, or maximum is taken over Y3. Similarly, F2 S2 capital F2 S2 equal to maximum of Y2 into capital F1 S1, and capital F1 S1 is equal to S2 minus Y2. From the last two, we can write F2 S2 equal to maximum of Y2 into S2 minus Y2, where maximum is taken over Y2. Now, if we use differential calculus to maximize Y2 into S2 minus Y2, then we see that the optimal value of Y2 equal to S2 by 2. That means Y2 equal to S2 by 2 maximizes the function Y2 into S2 minus Y2. Then by using Bellman's principle of optimality, we can write F3 S3 equal to maximum of Y3 into S2 square by 4, and which can be written as maximum of Y3 into S3 minus Y3 whole square divided by 4. So, again we use differential calculus to find the value of Y3, which maximizes Y3 into S3 minus Y3 whole square divided by 4. We find that Y3 equal to S3 by 3, that is equal to 5 by 3, actually maximizes Y3 into S3 minus Y3 whole square divided by 4, and this gives H2 equal to Y1 plus Y2, and which is equal to 10 by 3. Thus, we obtain Y2 equal to S2 by 2, which is equal to 5 by 3, and Y1 equal to 5 by 3. Hence, we find the maximum value of Y1, Y2, Y3. Putting the values of Y1, Y2, Y3, we get it as 125 by 27. Consider the following problem in which the objective or return function z is an additively separable function of n variables yj, and fj yj is a function of yj. Minimize z equal to summation fj yj, where j varies from 1 to up to n, subject to constraint summation j equal to 1 to n aj yj which is greater than equal to b. Here aj and b are real numbers, where aj is greater than equal to 0, yj is greater than equal to 0 and b is also greater than 0. This is an n stage problem where suffix j indicates the stage. Since values of yj are to be decided, so we may consider yj as decision variable. The return at the jth stage is the function fj yj. Thus, for each decision of yj, we have a return fj yj. We introduced state variables h1, h2 up to hn such that Sn equal to a1 y1 plus a2 y2 plus dot 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 an yn which is greater than equal to b. Sn minus 1 equal to a1 y1 plus a2 y2 plus dot 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 plus an minus 1 yn minus 1 which is equal to Sn minus an yn. Similarly, Sn minus 2 equal to a1 y1 plus a2 y2 plus dot 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 plus an minus 2 yn minus 2 which is equal to Sn minus 1 minus an minus 1 yn minus 1. And finally, S1 equal to a1 y1 and which can be written as S2 minus a2 y2. Let Sj minus 1 equal to Tj Sj yj, where j takes the value between 2 and n both inclusive. Then Tj can be termed as the stage transformation function, and it indicates that each state variable is a function of next state and decision variables. Let Fn Sn denote the minimum value of z for any feasible value of Sn, where Sn being the function of all decision variable. Therefore, we can write capital Fn Sn equal to minimum of f1 y1 plus f2 y2 plus dot 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 plus Fn yn, where minimum is taken over y1 y2 up to yn. First, we choose a particular value of yn and minimize z over the remaining n minus 1 variables. Therefore, we can write Fn Sn, capital Fn Sn, which is equal to Fn yn plus minimum of summation j equal to 1 to n minus 1 fj yj, where minimum is taken over y1 y2 up to yn minus 1. And this can be written as Fn yn plus capital Fn minus 1 Sn minus 1. The values of y1 y2 up to yn minus 1 for which the summation fj yj, where j varies from 1 to n minus 1 is minimum, keeping yn fixed, thus depend upon Sn minus 1, which in turn is a function of Sn and yn. Therefore, the minimum over all yn for any possible Sn would now become capital Fn Sn equal to minimum of Fn yn plus capital Fn minus 1 Sn minus 1, where minimum is taken over yn. If the value of Fn minus 1 Sn minus 1 is known for all yn, then the function to be minimized would involve only a single variable yn, and this minimization can be done by using any simple method. If capital Fj Sj equal to minimum of Fj Yj plus Fj minus 1 Sj minus 1, where j takes values between 2 and n and both inclusive, and also f1 s1 equal to capital F1 s1 is equal to f1 y1. Now, starting with capital F1 s1, the recursive optimization is to obtain f2 s2, f3 s3 and so on, and finally we obtain fn sn, capital Fn sn for each feasible sn. Each time optimization occurs over a single variable. Now, we consider an example. Use dynamic programming to minimize z equal to y1 square plus y2 square plus y3 square, subject to y1 plus y2 plus y3 is greater than or equal to 15 and y1, y2, y3 is greater than or equal to 0. To solve this problem by using dynamic programming technique, we define the state variables s1, s2, s3 as follows. We take s3 equal to y1 plus y2 plus y3, which is greater than or equal to 15, s2 equal to y1 plus y2, which is equal to s3 minus y3, and s1 equal to y1, which is equal to s2 minus y2. Now, we define the recursive formula capital Fj Sj equal to minimum of Fj Yj plus Fj minus 1, capital Fj minus 1 Sj minus 1 for j equal to 2 and 3, and F1 S1, that is capital F1 S1 is equal to F1 Y1. With this definition, we get F3 S3 equal to a minimum of Y3 square plus capital F2 S2, here minimum is taken over Y3, capital F2 S2 equal to minimum of Y2 square plus capital F2 S2, where minimum is taken over Y2, and finally capital F1 S1 equal to Y1 square, which is equal to S2 minus Y2 whole square. From the last two equations, we get F2 S2 equal to a minimum of Y2 square plus S2 minus Y2 whole square, where minimum is taken over Y2. Now, we use calculus method. To find the value of Y2, which minimizes Y2 square plus S2 minus Y2 whole square. And we find that the value of Y2 is S2 by 2. Hence, F2 S2 equal to S2 square by 2. Now, capital F3 S3 equal to minimum of Y3 square plus capital F2 S2, where minimum is taken over Y3, and which can be written as minimum of Y3 square plus S3 minus Y3 whole square by 2. Now, we again use calculus to find the value of Y3, which minimizes Y3 square plus S3 minus Y3 whole square by 2, and we find the value of Y3 as S3 by 3. Hence, capital F3 S3 equal to S3 square by 3, where S3 is greater than or equal to 15. Since F3 S3 is minimum for S3 equal to 15, Therefore, the minimum value of y1 square plus y2 square plus y3 square is 75 and y1 equal to y2 equal to y3 equal to 5. Let us consider another example. Use dynamic programming to show that z equal to p1 log p1 plus p2 log p2 plus dot 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 pn log pn subject to p1 plus p2 plus dot 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 pn equal to 1, where pj is greater than equal to 0 is minimum when p1 equal to p2 equal to dot 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 equal to pn equal to 1 by n. The problem here is to divide unity into n parts so as to minimize the quantity sigma pi log pi, where I takes values from 1 to n. Let fn1 denote the minimum attainable sum sigma pi log pi. Then for n equal to 1, that is in stage 1, we have f1 1 equal to p1 log p1, which is equal to 1 log 1. Now, for n equal to 2, here the unity is to be divided into two parts p1 and p2 such that p1 plus p2 equal to 1. We take p1 equal to x and p2 equal to 1 minus x, then we have f21 equal to minimum of p1 log p1 plus p2 log p2. If we put the values of p1 and p2, this is minimum of x log x plus 1 minus x into log 1 minus x, where 0 less than x less than equal to 1. And this can be written as minimum of x log x plus f1 1 minus x as f1 x equal to 1 minus x into log 1 minus x. In general, for an n stage problem, the recursive equation can be obtained as fn1 equal to minimum of p1 log p1 plus p2 log p2 plus dot 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 plus pn log pn, and which is equal to minimum of x log x plus fn minus 1 1 minus x, where 0 less than x less than equal to 1. Now, we have to solve the recursive equation. We will start with n equal to 2. The function x log x plus 1 minus x into log 1 minus x attains its minimum value at x equal to half, and which also satisfies the condition 0 less than x less than equal to 1. Thus, we find f21 equal to half log half plus 1 minus half log 1 minus half, which is equal to 2 into half log half. Similarly, for stage 3, the minimum value of the recursive equation is obtained as f31 equal to a minimum of x log x plus 2 into 1 minus x by 2 log 1 minus x by 2, where 0 less than x less than equal to 1. Since the minimum value of x log x plus 2 into 1 minus x by 2 log 1 minus x by 2 is attained at x equal to 1/3, which also satisfies the condition 0 less than x less than equal to 1, we have f31 equal to 3 into 1/3 log 1/3. Therefore, we see that the optimal policy is like p1 equal to p2 equal to p3 equal to 1/3. In general, for n stage problem, we assume that the optimal policy is p1 equal to p2 equal to dot 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 equal to pn equal to 1 by n, and the maximum attainable sum is equal to n 1 by n log 1 by n. This can be shown easily using mathematical induction. For n equal to m plus 1, the recursive equation becomes f m plus 1 1 equal to minimum of x log x plus f m 1 minus x where 0 less than x less than equal to 1, which is equal to minimum of x log x plus m into 1 minus x by m log 1 minus x by m. And since the minimum of x log x plus m into 1 minus x by m log 1 minus x by m is attained at x equal to 1 by m plus 1. So, f m plus 1 can be obtained as m plus 1 into 1 by m plus 1 log 1 by m plus 1. Hence, the required optimal policy is P1 equal to P2 equal to dot 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 Pn equal to 1 by n, and the minimum attainable sum is equal to n into 1 by n log 1 by n. In this module, we have discussed the basic concept of dynamic programming, basic terminologies of dynamic programming, characteristics of dynamic programming, and dynamic programming algorithm. We have also discussed dynamic programming module 1 and module 2, and we have taken some examples to demonstrate these models.